G'day everybody and welcome back to my channel. I've been having a little bit of a think, well should I say last night after I finished working in here and I left to go to bed and eat and whatnot, and I was sitting on the couch relaxing. I was having a think about what I'm going to do next. Now, I think what I'm going to do is I'm going to take out one of the references, the same one that we've taken the caps off basically, and put a zener in there, see if there's still oscillation, because then I'll know if I've got oscillation coming from the op-amp circuitry getting fed into the reference, or is it actually the other way around, the reference is oscillating and it's getting fed into the op-amp. Because to be honest, it could actually be either one of the two things happening. It also could be both an op-amp and the reference are oscillating, and there are waveforms of both interlaced onto each other. So I think I'll just stick a zener in there and just see what it looks like with a zener in there, just for curiosity. And then I think just start compensating everything with a blanket approach. So, basically large values of R's and C's to start out with, filtering op-amps, going from the output to the negative inputs, RC's across the inputs, stuff like that. Starting out with large values and just starting at the start of the circuitry, working our way to the end of it, and just looking on the scope as we go along. Like I said, blanket approach, we'll put big values in there first and move along until we get rid of everything. And then we'll start making values smaller as we, work our way backwards, if that makes sense. I can't really say where we're going to start and where we're going to finish yet, because I honestly have not even fully worked out how this thing works yet. Like I said, obviously it's a power supply. Obviously one op-amp monitors voltage against a reference, the other one monitors current against a reference, but there's a total of 8 op-amps in there and 4 references. So for each channel there's 4 op-amps, and is it 4? 1, 2, 3, 4 on each channel. One of those op-amps is driving the panel meter, so that leaves the other 3 to do the business, so to speak. So, and then there's the 2 references, right? And a bunch of transistors also on different boards. So there's some interesting circuitry in there, and I honestly haven't reverse engineered it yet, so I'm not going to pretend that I know what order things are in, because that would just be lying. The other thing I'm probably going to do at the end, I've been thinking about it, those little 10 nanofarad capacitors that are across the rails. In the old days, people used to go by, I don't know if it's so much theory, because capacitors now have so much lower ESR and better frequency characteristics with all the different types of capacitors we make now, that back in the old days you'd get say 1,000 microcap or 100 microcap, and you'd put that in parallel like an electrolytic. You'd put that in parallel with say a 0.01 and a 0.1, and to cover a wide range of frequencies in your filter. Nowadays you'll see just the bulk electrolytic cap and a 0.1. Sometimes you'll even just see a 1 microfarad cap, like a small, like the little ones I was using on the op-amps, these little multi-layer monolithic chip capacitors. They have excellent frequency characteristics, and just one of those does the business, right? So something I might end up doing is, or will end up doing, is after we have compensated everything and gotten rid of all the problems on it, I'll probably change those 10 nanofarads to 0.1s. I don't think I'll put 1s in there, because that actually could be high enough to actually cause a bit of a low frequency oscillation on startup between the transformer and the 1 mic caps on the opamps. I don't know that would be the best idea. I already put some in there, but I put them in there with bigger electrolytics at the same time, and that made things worse. But I honestly think it was the 1 mics that made things worse. So I'm probably going to put 0.1s in there because, you know, low ESR electrolytics and 0.1s versus non-low ESR electrolytics and 10 nanofarads. So I don't know if you get my thinking there, but just it's how we do things now. It's going to have a lower ESR over a wider range of frequencies, so it's going to do a better job. Right, so anyway, that's the order. I wrote a little list here so I didn't forget when I came in here today what I was going to do first. I thought I might have written something else on here. Just checking. No, that was it. So, try Xena in there first. See what that waveform across that reference looks like. And yeah, go from there. Start trying to compensate opamps after we work out. Well, let me say this. First, obviously, we have to work out, is the oscillation coming from the reference or is it coming from somewhere else? If it is, I still want this to be reference based, so I'm going to try and knock that out. Got a number of different ways of doing that. I've got higher accuracy, lower current parts like the ATL 431BQ DZR, the little surface mount ones I've got. They're the B type, so they're 0.5% accuracy, I believe. Actually, I can just have a quick look. I've literally got the data sheet loaded up. Yes, 0.5% accuracy, and they go down the IKA, the cathode current minimum, 35 microamps, and IRF, the reference pin current, 150 nanoamps. Now, if we all remember the TL431B in the TO92 package, minimum cathode current for regulation is 0.4 milliamps, right? And the, reference input current, 2 to 4 microamps. I'm just looking to see if there's any minimum reference current. Not seeing it. So yeah. So anyway, the point I'm getting at, obviously, microamps, nanoamps, and what was this point? Sorry, I forgot what I read. One moment. 0.4 of a milliamp, typical figure for minimum cathode current regulation on a TL431A. So what's that? 0.4 milliamps, 400 microamps. I'm having a brain fart moment trying to do conversion. I'm pretty sure it's more than 35 microamps. Anyway, the IRF is 150 nanoamps, and that's what concerns me more, because obviously the reference pin not having enough current there or having instability on the reference pin is going to cause the thing to go absolutely nuts. So having a part that's got higher tolerance, lower current consumption, and especially the 150 nanoamp requirement for the IRF, I just feel like that part's going to work in there better. Like the bottom board, as I said, it's 37 milliamp source for the two 5.1 volt references. The top board, it's 5 to 6 milliamps at the most. It's about 5 milliamps. One measures 5, one flickers between 5 and 6, so you can call it 5 milliamps. Anyway, like I said, it doesn't seem like the voltage supplying the dropper resistor and the current across the reference doesn't actually disappear when it goes into oscillation, so it's not a current problem. But for stability reasons, I'm thinking, if I can't make one of these, rock solid, because like I said in the last video, I can't just keep going up in capacitance because there's a dropper resistor that drops the current into the TL431. If I put a huge capacitor on across the TL431's anode and cathode, you have to wait for the RC time constant you know, the current's got to get through the R and then charge up the C, which takes time. And as I explained, if the reference is low, the voltage will be too high, and that will lead to overshoot, basically. Let me just see something, because currently I've got way more capacitance on one reference than the other. Let's just alright, so looking at the slave channel, yeah, okay, so at the moment with 47 microfarads it's actually alright, but if you wanted a quick demo, I could put a ridiculously big cap on there, and you'd see when I turn it on, the voltage would go up way higher and then come down as the cap charges up and the reference voltage comes back up, and that would be a problem. So we can only add so much capacitance to the reference, which is why I'm saying that I might end up using the other reference, because it might be easier to compensate that with less capacitance, you know. Also, there's also a few little tricks. If you've designed switching power supplies and stuff like that, and you use, look, in most of my switching designs, I use that's why I have the ATL 431Bs, because I just like the 0.5% tolerance and the smaller currents required for regulation. So that's my go-to part in switch mode supplies that have a TL431 in the design, or even like an LM335 or something. Is it 335? I always get it muddled up, but yeah, that's my preferred method. That actually, I do have supplies that I've built that have TL431s in the regulation circuits. I'm not saying that I haven't used them, but my preferred method is the ATL431B. So that's what we're going to do. Try Zener, see if the oscillation goes away across the reference. Will be a Zener then. If it does, we're going to put, well, I think I'd actually rather, honestly, now I know that the top board has 5 milliamps for each reference and the bottom board has 37. I think I would actually rather make the top two references out of the ATL 431BQ DZRs I have. Anyway, it just makes more sense. They're going to be able to maintain more accuracy with, you know, any fluctuations with that small current going to them. It's just going to be better. I'm not talking about the cathode current, I'm talking about the reference current, because, so the thing you got to remember here is you got a dropper resistor coming in. The pots that you use to set the reference voltage, if you have that too lower in resistance, to get more current to the reference pin, you're going to pull down the voltage and current from the dropper resistor to ground, and then you won't have enough cathode current, or not enough current at all, you know what I mean, or the voltage will be pulled down too much, or, you know, you can run into problems there. So yeah, anyway, I think everyone gets where I'm going with this, so enough wafting on. What I'm going to do now is I'm going to take the board out. Actually, what I think I'll do, because I'll just give you guys a quick look, because I've got this dead bug style TL431 with a pot on 2 pins and a cap tacked off of it. I think I'll just cut the pins and solder a Zener on top of it, because you guys have seen how old the board is. Even the areas where the board is good and it's not burnt at all, the traces still lift really, really easily. The old boards were constructed differently to the way we construct boards now. The glue was different, and it gets old, and it just doesn't hold the traces young when you get it hot. So I'd rather try and leave the bottom side of the board alone as much as possible for that reason. So I think what I'll do is I'll take this cap off, this 47 mic cap, and then I'll just cut this because I can just tack this back on if we decide to come back to this. But like I said, I think if I do have to end up trying to compensate a reference, I'm not going to be going back in with this with a bigger cap value. I'm going to make up 2 new ones with ATL 431s, Bs, ATL 431B. QDZR is just the rest of the package and everything. It's just the full name for the part that I ordered. But anyway, yeah. So I've got my 2 pins here now. I'm just going to tin the very end of them so I can just tack a Xena across them. Now, I've still got all these Xenas here that originally came out of it, so because that's the other thing, like I didn't mention in my last video, something else that I looked at in the data sheet. You know how it's on my phone. I'm a bloody idiot, aren't I? Actually, you know what? If I plug my phone in whilst I'm recording, I might be able to get file access because my phone's unlocked on my computer. Yes, I can, and I can show you the data sheet for these diodes. It doesn't say on the data sheet, I don't think, this is a soft knee diode, but just going off of, let's just wait until I find the data sheet on it. Right. Actually, I'm just going to move this to my data sheets on my computer because I actually want it on here. Right, I'm going to open that. Sorry, I just got to unplug my phone. So there you go, as I was saying, New Jersey Semiconductor Products. How old school, hey? As you can see, BZY88, C5V1, all the way up to C33 volts. Honestly, there's not going to be much difference because I'll tell you now, this is the diode that they're using for the 37 volt source, and the 3.6 volt diode was the one on the 5 milliamp source. And if we look at, yeah, see, IS milliamps 5. I'll just make that bigger because, yeah, right, they're all spec'd at 5 milliamps. So yeah, actually I wonder maximum Xena impedance. Oh yeah, no, because it actually also says here the regulation voltage at 8 milliamps. Well, that probably is 5 too. It's just really hard to read the text. But 4.8 to 5.4 volts. So I'd say they're a soft knee Xena, just looking at the specs here. They don't seem to have very hard characteristics and pump current, you know. Although they are half watt Xenas. Anyway, so I'll put one of those in here. Got to find one of the 3 volt 3v6 ones, and I do remember that one of them read the wrong voltage, so I'm just going to, actually this is going to take too long. I'll pause the video, get my power supply here, and I'll work out which one's actually working still, and I'll come back. Alright, so I've found it. One of them goes up to 3.68 volts at about 15 milliamps, 10 milliamps. The other one goes up to 3.9, so I've chosen the one that goes up, sorry, did I say 3.8? 3.68. So yeah, this is the good one. So I'll put that in. I don't know which end positive comes from. I guess there's an easy way of working that out. You've got to be shitting me. Seriously? Is that my meter playing games again? Oh, my meter's playing games again. It's like, how is there no voltage here? Right. Oh, it's exactly what I thought it was. I had a feeling it was this end because I marked a positive there, but me being an idiot, I always get anode and cathode mixed up sometimes. So I just wasn't 100% certain. I thought I'd just double check it. Make sure that the stripe on the diode actually does face this way where I put a little plus on the board, but not that anything would happen if I put it in the other way. We'd just have a 0.6 volt reference. I should probably turn this off, eh? Oh, that would have been interesting. Need a little bit more solder. Alright. 3.6 volt reference Zener installed. Quick sanity check. There you go. 3.368. As it's warming up, it's regulating. This is the exact reason why I chose to put references in here. Alright. Turn that off. Grab one of these. Stick that in there. I'm going to tin either side of the diode, just where the leg bends sort of thing, so that I can get my probe on here. Perfect. Let's put it on ×1. Alright, let's see what we have. Okay, let's load it down and see if that starts going crazy. Because then we know. Oh, I don't trust this thing yet, as you all know, so be careful. Yep, cool. Okay, well that's good news. That's really good news. You know what that means? Wow. Different waveform because it's a Zener. I think that's the opamps I think the references are in feedback loop of opamps already oscillating. So I think what's going on here is basically unloaded there. You're just seeing Zener noise. But man, I just dropped my shorting bar, if you can call it that. It's a bit of solder wick. That's either remnants of high frequency oscillation getting fed through, but I think that's a Zener noise. I'm not even too worried about that. It looks exactly the same as what the reference did when it was unloaded. So I think that is coming from somewhere else. I don't think you can see the Zener noise through that, because Zener noise isn't that large. I mean, it can be, but I don't think it would be a 5 milliamps on a 3.6 volt Zener. But I could be wrong. But the fact that when I load it, it changes like that, and the oscillation breaks out into different forms. just as it was with the TL431 in there. I think we can confidently put the references back in. So that's good. And as we saw with the references, I put 47 mic caps on them and that cleaned them up a lot. I tried holding one mic MKT across it and that cleans up a lot too. So I think what I'll do is I'll put them back in with 47 mic caps and 1 microfarad MKT. The annoying thing is I made these modules up with the capacitor being the legs. I can't take it out. It's just gonna be a bitch. I think I might just cut the capacitor off. Just tack another one on. Not tack another one on. I'll put it through holes, the next set of holes, and then bead another 2 blobs of solder across it. It's just perf board. I think that's what I'll do. So I'll do that now, and then I guess we just start trying to compensate op amps. Well, I'm actually quite happy because I thought I might see some sort of a change and, you know, discover that we actually have 2 sources of oscillation. You know what? Just before I do take that out, I just want to see one more thing. Let's have a look on this crappy Finersi scope, which comes in handy again, with it, because this is not mains reference to Earth. I just want to see if it has a difference. Alright, we're still set where we were before, cool. Interesting. Either this scope really doesn't show jack shit. Oh shit, I keep hitting down. Yeah, right. Alright, let's load the supply and see what happens. I can't trust this scope, eh? You know, I shit you not, the scope in this little thing is better. That's why I put a BNC jack on it. It literally performs better than this heap of crap. The only thing I've actually found this thing useful so far is looking at literally just a quick look at an audio signal to see if it's there. It's actually got some, you know, peak to peak to it. And timing signals on cars I've been fixing when I've been wanting to match up a crank sensor with a cam sensor, for example, and stuff like that. I found it handy for that because it's only 2 channels, so it's still not too handy. Sometimes I do have to take that out when I need to match up more than 2 sensors, but yeah. Let's have a quick squeeze on this, because this component tester has a scope in it. Also Finersi crap, but I guess better Finersi crap. The bandwidth on this is limited to like something ridiculously small, but as you can see, I don't know if you can see, you can already see a signal on it. I don't know, this just has lower, what do you call it, higher resolution voltage wise, like volts per division, it goes down lower. One thing I will tell you is that where it says 10 millivolts of division there, that's bullshit. It actually only goes down to 20. The 10 millivolts is software driven sort of thing. But anyway, you see how much more shows up on there. And this thing's only limited to like a couple 100 kilohertz bandwidth or something. So anyway, we know that we do have a problem there. It might look a little bit different on the scope because it's creating an earth loop, and we're probably seeing some of that come through too. Yeah. that's probably what all those little lumps are that you see at the top there, that's interlaced onto the noise. That's the like half rectified 100 hertz coming through because of the ground loop. So we can ignore that part of the waveform, we know what that is, and I've already proven that in the last video on the opamps too, so that's good. Alright, time for references to go back in, just a little bit different this time. So now I've got to think about how I want to do this. Do I want to just keep using the TL431s? Do I want to use ATL431Bs? I think, yeah, I'll just go from scratch with ATL431Bs. I think what I'll do is I'll stop the video here because I'm going to go, I still haven't got, I'm going to take Tanmera Tech suggestion and order some ferric chloride and try that for my etching, because I was having really bad luck with like literally the last 6 batches of ammonium persulfate, and I still can't work out if it's contaminants in the tap water, in the dish I'm using, what it is. If I think the chemical I'm getting is no good, but apparently ferric chloride works like basically with any water, so I'm going to try that. It's just a lot more robust and works better. But point I'm getting at is I'm not going to try and etch a PCB right now because I've still got the same shit that doesn't work. I do have a couple, okay, I've got a solution here, that's fine. Alright, here's my, so I'm just trying to choose the 2 neatest ones because these are just for testing. I did make these little SOT23 breakout boards that I etched, just out of leftover board from other etchers, so I didn't waste. That's what I do with all my board offcuts. I use it to make breakout boards. It's very, it's a good idea. It's, you know, you cut a board down and you're left with all these little strips and stuff. Make breakout boards out of that instead of throwing that away. I think what I'm going to do is I'll mount my surface mount ATL431s in the SOT23 package to this, the 2 of them. You know what? I can't remember what pin is the reference pin. I might be able to tack the pot literally across that and a cap across that. I might not even need to put that on another like bit of perf board or something. Let me just have a look at the pin out. Reference cathode, anode. Doesn't really matter, I guess, really what order they're in, because they're sort of in a circle. I mean, it's not a circle, it's a triangle, but the pins go around, right? And the pot's got 3 pins that are like that, so you can rotate it to match. So, yeah, I think I'll do that. I think I'll mount the 2 ATL431Bs to these 2 boards. Put another 2 of those little trim pots across it. And yeah, the 1 mic MKT and the 47 mic electrolytic, and I mount them as close as I can to it this time. Last time, well, the electrolytic cap I mounted as close to it like you should, but the MKT was an afterthought, so it got tacked on the other side of the board, which is all the way at the other end of these leads. Although there again, it might actually be better there because, no, I'll just do it all on the one thing. I'll try and keep both caps as close to it. Alright, well, I'll go do that. I'll stop this video because I join my videos together, and I'll come back when that's done, so I don't keep you guys watching for too long. You know, I was just pulling everything out. I just realised, sorry, my hand's blocking the microphone. I've already had my first silly moment of the day. I was literally just looking at the panel meter at the voltage, saying, you know, if I put too big a capacitor on that reference, the voltage is going to come up too high and then come back. That's the current reference. The current's going to do that, not the voltage, which is obviously equally as big of a problem. So I don't know how I didn't think of that. Oh God, you know what? You know what this means? We're going to have to do this again. Because I'm going to have to put that reference in with the 47 mic cap on it and put a load on it at startup and see if the current overshoots for a bit. Because I'm already suspicious that 47 mic is too much. If you all get where I'm going with this. If not, just bear with me. I'll just pause the video whilst I make the connections. Alright, I've just done another little Jim Williams dead bug style module. We're going to put this on amps. Let's do, well, did you see that? But that could be oscillation too, we don't really know. Or did I just put that reference around the wrong way? Let's just see something. No, I didn't put the reference around the wrong way. Hold on. Yeah, no, that's 1 amp. Okay, the reference is working with a 47 mic cap on it. So let's put the current at, say, I don't know, 400 milliamps. Let's turn it off. I'll short the cap out just to make sure it's discharged. Let's see what happens. Okay, I don't think that was, I think that was putting out the whole, yeah, 12 amps. I can feel the resistor getting warm. Okay, that's not gonna be a good way of testing it. That's really annoying. Yeah, actually it doesn't overshoot, it's just oscillation. So 47 mics, okay. Alright, well that's good. Okay, ATL, so that's what it's going to be. ATL 431B, 47 mic electro. Have I got any low ESR ones? I'll go away and I'll work all this out off camera. And I'll come back with my solution. Alright, I'll be back soon. You know, something else I just carried to, which is a bit concerning, because the entire time I've had this thing, I've always wondered if someone's done something, because there's solder on one of these lugs here, and like I said, it's just a bit strange how when you change the two constant current pots, one you can put a 5k in there and it still works, the other one you put a 5k in there and the voltage changes. It just, both sides are supposed to be the same. I don't get that. That's within independent mode. That's what really throws me. And then I was just thinking about this, the transistor that's been replaced has been replaced from a 60 volt part to an 80 volt part. Incidentally, on the slave channel. The slave channel was the one that when I got this had the 20k pot where the 10k voltage set pot should have been, and you could turn it up to 55 volts. Now I'm wondering, did someone actually modify this thing so that one channel went up to 60 volts and one channel went up to 30? It kind of makes sense because of where it came from. This, where's the name? The tag. Yeah. I don't know if anyone here knows about telephone lines, but 30 to 60 volts is basically the region for the old telephone lines. I can't even remember what it's called. You know, you twisted pair and 4-pair cables to red, white, blue, black, red, black, blue, white. You know what I'm talking about. Old school telephone cable. You plug your dial up or ADSL 2+ modems and that sort of stuff into. Well, if they were working on that sort of equipment, maybe the guy that owned this modified one channel. Food for thought, eh? But it's got me thinking. And there is differences in oscillation on one side to the other, which also has me thinking, because if they're two identical circuits, you'd think... I mean, I guess high frequencies oscillations can be pretty erratic, but I mean, I don't know. It just makes me wonder. I won't be surprised if eventually we have another aha moment and find out that something is changed from how it should be. But we'll know when we get there. I've been having a think about these references that are just flapping around in the breeze. I think what I'm going to do is, because they go in between... Wait, does it actually connect? Yeah. Because they go in between those two traces you can see through the board there. I'm just going to drill a few holes, like a row of 3 holes and a row of 2 holes and another row of 2 holes. Then I can just put a TL431 and a couple of capacitors in there, and just on the bottom of the board fold the leads over to form the traces and solder the leads to those 2 traces. I hope that makes sense. Oh, and the trimmer pot, or maybe the trimmer pot will just get tacked across the top. I don't know, I haven't thought about it yet, but I definitely want to try and incorporate it into the board somehow, so it's not just flapping around the breeze. That way I can minimize the inductance on the leads going to it, because it's probably getting its power supply from something here that's smoothed by a cap, and then there's inductance going to that, and then it's doing its own regulation with a cap in there that's could cause a seesaw effect. So, and for oscillation reasons, with it going into input of an op amp, it's also better to have it as close as possible. So I think before I come back and make more video, I think I'm going to convert these two to ATL431s, and I'm going to keep these ones as TL431s because high current, they're alright, but I'm going to put them on the board, and I'm also going to put 47 microfarad caps with 1 microfarad MKTs on them. These already got the MKTs on the back of them, but they've only got the 4.7 mic cap inside there. So that's my plan. And then we'll come back, have a quick look at what's going on. I mean, honestly, there's not even really any point, because from what we've seen, whether the Zena's in there, the reference is in there, a better compensated reference is in there, the oscillation's obviously coming from the constant current circuit op amp, and yeah, so might as well just, now we know what works out best in this thing, do that to all of them, like what I just said to the bottom 2 and what I propose to do to the top 2, then come back and just start compensating op amps, basically starting obviously at the beginning with the ones that look at the inputs, and moving our way forward to then those ones, and then last but not least those ones. So that's the plan. Alright, I'll be back soon. I've got some house cleaning stuff to do, so I've only come in here over the last couple of hours when a few things popped into my mind that I just wanted to add to the video. and to my notes. So I'm going to go finish vacuuming now and then come back and knock all this up and we'll go from there. Right, so I'm just getting started selecting components. I'm back in here now. Just grabbed a couple of those ATL431Bs out my stash. That's them there. And I was thinking about something. It's actually kind of funny that it's going to work out this way, that the constant voltage references are 1% parts and the constant current references are 0.5% parts. Because, you know, combined with decent opamps, that makes a pretty decent power supply. And usually you have more accuracy on the voltage than the current on a power supply anyway. So, I mean, it doesn't really matter exactly how accurate the reference voltage is, I guess, because you're just comparing the output voltage against a number, really. But, you know, still, it works out current wise a lot better, like I was saying before too, because these take a lot less current, especially on the reference pin. So I'm hoping that's going to make it easier to compensate it. I'm not going to do all this on camera because I'm going to go through holes and whatnot, but basically what I've decided, I'm going to salvage the parts off of these two boards in my own time, and I'll put them back away in my drawer. What I'm going to do is I've got to salvage two of these boards anyway. This will take less time because it's not wrapped up, so I might just do these two. But no, I'll do these two. The pot's already set where I want them. I'm going to take the TL431 out. I'm going to sit it basically sideways, so that one pin there, one pin there, one pin there, more closer to there really. And then I can run one pin over to one track, you know, like the cathode, the anode over to the other track, and then the reference up to the wiper of the pot, and then one of its pins over again to the track that the anode and the track that the cathode's on. And then that leaves me still all this space here to add capacitors to it, leading up to the input of the op-amp, which you want the capacitors in between the input of the op-amp and the reference, not before the reference or on long wires away from the reference or something like that, you know what I mean? So that kind of just works out perfectly. So I'll do that off camera because it's going to take drilling and mucking around, and I don't want to bore you guys. I'll just come back and show you when I've done it. And as for the top two references, like I said, I'm going to use these guys, the ATL431Bs. So, yeah, I'll be back soon. Alright, so this is my solution for the TL431s, just the normal TL431As. I don't know if you can see what I've done there. That's the pot in the TL431, and that's how I've wired it up in between the two tracks, like I said I was going to. Now, because there used to be a Xeno diode across those two holes there, that leaves a free hole there and a free hole there, and I've drilled another two holes there. The reason I've done it like that is when I end up getting the exact capacitor values I want to... You right? Hello? You right? What the fuck is my cat doing? What are you doing? You're weird. Anyway, so I can fit one capacitor in between there, and the other one there, and probably just fold it over or something. If not, I can always put them on the back of the board. There's plenty of space on the back. So, but the main reason I've done that and not put the capacitors on yet is so that I can tack them on the back. And if I'm experimenting around, I'm not going to have to keep desoldering and ruining traces. I can just tack them on, untack, you know what I mean? And once I've got the correct values dialed in, then I'll mount them through the two holes I've drilled and the two pre-existing holes where the Xena was. But yeah, that's what I've done to get the TL431 integrated into the board. I'm happy with it. might not be the neatest thing in the world, but I don't think it's the ugliest thing in the world either. It's all solid. It's a lot better than the way I had it, just flapping around in the breeze on the wires, so I'm happy with that, you know. And the trim pots are facing up, so that's nice and easy to set them to whatever, you know, I want to set them to. That'll be about 10 volts in the middle, so I'll leave it there because I'll set this on my power supply. Right, so I'm gonna go. I'm just thinking. Pause. Can you not? You're being annoying. I'm just trying to think what the waveform looked like. I remember we looked at the bottom Zenas and they weren't as much of a problem. Pause. Get out of here. They weren't as much of a problem as the top ones. I think we just saw that high frequency sort of oscillation, Zena noise, whatever it is. I don't remember if it got bigger or not. I'm going to go off in, like, now when I stop this bit of recording, I'm going to watch that video and just refresh my memory. Because if they were fine how they were already, I'm just going to put, maybe I'll up the cap to say a 10 mic, and one of these I'll put there and just leave it, you know, if it was already fine. And set the voltage to 5.1 volts on them and be done with it. If not, then I'll leave the caps off and we'll investigate that too. Because, like I said, I'm going to go through everything, the scope, and compensate everything. So what I'm going to go do now is make up the ATL431B boards for these two for this board now. That's the two holes where they come out of, so I'll work something out for that now and come back and show you what my solution is, and then we'll put it all together and start working out. Well, first thing I'm going to do is work out basically under the conditions it's already under, just try and make the TL431s quieter without going too crazy high in capacitance, because like I said, it'll screw things up when it gets turned on and the reference doesn't charge up quick enough. Essentially making it a low voltage reference, lower voltage than what it's supposed to be. You all know what I'm trying to say. Yeah, so I'm gonna go make up these now. I'll come back, we'll sort it all out. Actually, I'm going to take this board and dial in the two references at 5.1 volts first before I forget. But yeah, I'll be back soon. If anyone noticed, don't worry. I just found out the hard way. Just went through a very long, why on earth can I only set the voltage on one of these, not the other, when they both wired up correct and I know they both work. Yeah. Apparently I didn't solder one of the connections. I've done that now. Just wanted to point that out so no one watches the video and starts worrying. Don't worry, I found it. I'll go set the voltage on this one now. That's set at 5.1 volts. I just got to set this one at 5.1 volts. I'll be back soon. Right, so moving along, I got both of these dialed into 5.1 volts. That other reference, I blew it when I tried to power it up with one pin unsoldered. That happened to be the reference pin. No, the reference pin was connected to the pot, but only one side of the pot was connected to the rail, so the whole positive voltage went in the reference pin and cooked it. So I then stuck it in my breadboard and had some fun with it. Probably shouldn't have done that because now my breadboard's fucked, but whatever. So this is what I've come up with. These are the small breakout boards that I make for these little devices. If you turn it around that way, that's the reference pin. Sorry, that's the reference pin. That's the cathode, that's the anode. So I can literally just put the pot straight over the top of it like that, which is what I've done here. Sorry. like so. And then that will just have 2 legs coming off of it, which I'll make up out of some thicker wire this time, because last time I used resistor leads and the boards were a little bit flimsy, to be honest with you. I'll use some nice thick wire, like what I had that pot and TL431 mounted on, that was just on its own without caps that we tried. So that's what I'm going to do for the top 2 references. These 2 little modules, micro modules, I don't know what you want to call them. I'll be back soon. Okay, so I've made those references up, mounted them as flush to the board as they go. Actually looks quite neat if you ask me. They're soldered in. So there's space to tack capacitors across here on the back and across there in this little space here on the front. So both of these onboard now references have got plenty of space to add capacitors. So what I'm going to do now is we're going to put this together, and basically I'm going to hook up a scope probe to each reference, like one probe to this reference, one probe to the other reference, not the other side, like one constant current reference and one constant voltage reference. And what we'll do is we'll play around with capacitor values until they get up to the point that I don't want to go any bigger, basically, and then leave them there, and then we'll go and start compensating the opamps. We'll probably come back to the references later and see, after the opamps are compensated and not oscillating, if the references still need such big capacitance values. But for now, just to help, I'm just going to put whatever. I don't even want to put 47 mic in there, so when I say big, I don't mean that big, you know, but we'll work that out now. So I'm going to put this together and get it in the power supply, and I'll be back. Alright, I've just decided upon one more thing before I go ahead and put this all together. Since I'm going to be doing compensation on the opamps, I'd rather have everything how I intend on leaving it for its final state. And I've weighed up my options, and I think what I'm going to do is I'm going to put 0.1s right across each op amp. So that board's only got 2 op amps, that board's got 4, so that board's got 6. Give me a sec, my cat's just knocked something over. Guess I'm going to find out what that was later, because I just heard a whole load of crash sounds in my house and I can't see what it was. I'm sure later on I'll discover something in my kitchen. Actually, I've got a back room that's full of tools and stuff, so I've got a funny feeling that it's that. But anyway, this is what I'm thinking. And obviously I'm going to remove the 10 nanofarads again. Look, I genuinely think that these are the bypass caps they use for the op amps. That's what I think they're for. And like I said earlier on, that was just the old way of doing it. I'm going with 0.1s. Yeah, well, I don't have much more to say on that, so without further ado, I'm going to install these, then I'm going to put the boards together, then we're going to start scoping stuff out. We'll see what we can do. Alright, so I'll just show you guys just one last quick view before I put all this back in. So I've put the 0.1 microfarad monolithic capacitors on each op amp. And we have our, if I can get this to focus, there it is, the ATL431B on the little board with the pot on top of it. And for these ones, we've got TL431As and a pot. So I'm going to put all this together now, and then we'll start scoping stuff out and working out capacitor values, RC, network values, all that good stuff, and try and get it to, you know what I want to say, eh? Shut the fuck up. Because it's making a lot of noise. So yes, let's see if we can get it to do that. I'll be back soon. Alright, it's the next day now. I've had to play around with this. I actually filmed me playing around with it for a ridiculous amount of time and deleted the video because I wasn't just gonna, it was almost an hour and this video is already an hour as of me talking right now. It's about an hour. I spent so much time. See, the thing is, this thing's got that many different windings on it. Some circuits, obviously all the different circuits are referenced to each other in one way or another, whether like a reference circuit is referenced to the positive terminal or the negative terminal, and then that goes back to an op amp, and the output of that goes into another op amp. Obviously everything's all connected, but when I probe things around, I like to try and look in between like the 0 volt point of the power rail or the center point of a power rail and the device's inputs or outputs or whatever. So anyway, actually this will actually answer someone's questions in the comments too, because someone asked me where my ground probe's been connected to, and well, that is not really something I can answer with one answer. So right now I've got a ground lead plugged in the front of my scope. I've actually got it on the negative terminal. I could also put it on the positive terminal because what I'm looking at right now is referenced to basically everything. But here's the thing. Sometimes, let me just grab this probe I've made. Because as I've shown you guys, I've made these probes where I've minimized tip capacitance and I've soldered a very small, so I can solder that directly across things. So if I'm, like the references for example, one end of them goes straight back to a power rail, like straight back to a capacitor from the power supply, the rectifiers and the transformer. So in that case, I'll be soldering the ground to the power supply rail and the tip to the cathode. In other situations, like op amps, sometimes I'm doing this. I'm looking from the output of the power supply, like the negative terminal, and the output of the op amp. Other times I've tried having a look across op amp rails. That's why I got this little bit of blue wire sitting here too. Let me just take this probe off the board so I can show you what I'm on about here. One moment, soldering iron's just coming up to temp. Oh, you can all see that. Yeah, it doesn't take too long. There you go. It's up to 350 now. Oh, no, it's only 270. I just saw the 50 on my camera and I thought I was there. Right, 312, 320, 330, 340, 350. Alright, so right now I don't have anything on the ground on this probe. I've just got the tip of it coming out because I'm using it in conjunction with this ground lead that's going back to the ground on the scope. But I also sometimes, like when I've been looking in between an op amp's power rail and its input, I've been soldering this piece of wire on here and soldering the wire to the power rail and putting that on the input. And like I said, in other situations where it's like a reference or something where one end of it goes straight to a power rail, I will solder straight across it like this. Sorry, that's not focusing. Man, hold on. Whoa, I just realised the whole screen's blurry. What the hell? Oh, I must have touched the screen. Shit, I hope that wasn't like that for too long. I'm sorry. The autofocus, I touched the screen, put the autofocus back. Anyway, yeah. So the point I'm getting at is, no, I haven't been very clear on where the probe ground is connected to because it's been connected in a multitude of different places. That's why. But so now you know what I'm doing. I guess the person that asked me this already knows why, but other people who might be wanting to learn probing techniques and all that, the reason for this is basically if you just connect a scope probe anywhere across anything. So say I was looking at a reference and I put the ground on the cathode and the tip on the anode, well, my probe would be looking at the power supply rail for starters, and for second, the ground could be doing a number of things to the cathode. It could be introducing mains hum there, it could be causing a ground loop, it could cause the thing to go into oscillation. If it's reference to ground, it could be shorting it. So you've really got to think about what part of the circuit you're looking at as to exactly how you're going to hook up your ground probe. I can already tell you the thing that's really been hard for me with this supply is already even just grounding to power rails and the output, I've run into problems where I'm getting inconsistent measurements. So let me think of a good example of this. Oh, you know what? Actually, I wouldn't say it's inconsistent measurements because the little scopes that I tried using, last night, I was getting inconsistent measurements and I thought it was ground loop problems. And so I got my little battery tablet scope out and I tried that, and then I tried the little one that's got a smaller bandwidth but seems to work better in terms of triggering. And well, I got different results on them to this, which is obviously mains coupled. So I don't know, like I said, this supply is kind of built upside down and everything's referenced in a weird manner. So it's kind of, I don't know, maybe a couple of times I have put the ground probe on somewhere wrong and caused a problem, and that's why I've gotten different readings. But then I was thinking about that last night, and also when I was reading over Andy's comment in the comment section, it made me think about it again this morning. So I came in and I thought, well, because one of the main things I was having trouble with was I was looking at the output of this op amp just up here, which is, it's got the reference going into one input of it, and the other input has it eventually goes back to some resistors that go to a resistor that goes to the voltage pot. Okay, so I think that's the one that sets, yeah, okay, the reference goes in one side of this op amp and the voltage set pot is on the other side of it, basically speaking, but they're interlaced in a way that I guess the voltage pot boosts up the output of the op amp so it amplifies the reference, and then that is fed down here and compared to one of the inputs on the constant voltage monitoring op amp, and the other input's obviously looking at the output voltage. So that's how the constant voltage circuit's working. So there you go, finally traced something out for you. Well, now we know I guess that's how the constant current circuitry is working too, and we already know which op amp and reference is. Actually, we don't know that. That's actually a freaking good point. I have not considered that. Because on the top board there's only one op amp, and that op amp powers the panel meter. So maybe the constant current reference is just directly on one input of the first op amp that looks at the constant current sense resistor. I don't know. Yeah, maybe they have got the reference divided down and going into one input, and then the current shunt going into the other input and a pot across the reference. That actually makes sense because I remember now when we measured across the pot, the constant current pot, I'll show you guys actually, it's got a really small voltage on it in terms of across it. And the constant current reference is 5.1 volts. So this pot's not, if I can just get my probe in here, this pot's not, what do you call it? It's not dividing down the 3.6 volt reference because it's only got, really? 0.765 of a volt across it. It seems a bit low. Let me just see if my current's gone up and it's putting out more than 1 amp when I turn it up. Because that would explain that. If the reference has gone up low, the current limit's going to be higher than what it should be. Sorry for all the faffing around, but I've really got to work this thing out. It's just going on too long. No, it's set perfectly at 1 amp. So, that's interesting. Maybe they're dividing down the voltage off the current sense resistor a little bit. A lot of designs do that. Sometimes it's divided against one of the rails and then tapped off of that. It's to sort of get around leakage currents that are flowing through other places, like from the constant voltage circuitry and stuff like that. More accurate, but usually you do that with a separate op amp. Like in my power supply design that I've designed, the one that's really low noise and it's constant voltage at the moment, and I haven't finished the constant current because I'm trying to finish a few other little things like a little power supply in it that controls fans and panel meters. It's too noisy and panel meters were oscillating, so I'm held up on that at the moment. But the current section in that, what I've done is I've got current sense resistor on the positive rail, op amp looking at that. Then I've got a reference, and basically that reference is adjustable, and then I've got another op amp that's looking across a little 1 ohm resistor that's in series with all the voltage feedback circuitry and tap changing circuitry and all that, so that I can look at what I'm calling leakage current to the output terminals, and then all that goes back to another op amp, or no, 2 op amps. One deducts the leakage current from the main op amp's sensed current from the shunt resistor, and then the 2 of those outputs go into another op amp that does some summing, or I can't remember how I've got it, but I think I've got 1, 2, 3, 4 op amps in my constant current circuit, but it's a insanely accurate circuit. So it's a bit different to this one. This has less accuracy on the current side. The constant voltage side is done really well. But yeah. So that brings me to what I am doing today. I feel like I just missed something out that I was explaining then, but oh well. I think I covered everything I wanted to say. Anyways, so I'm starting to get the suspicion. I had this suspicion from the first place, but I just never said nothing about it. The op amps I put in here are jfet op amps. They can be faster or slower than the LM301 technically. It depends on your compensation resistors. And I don't just mean resistors, networks, capacitors. I don't just mean about the compensation capacitor you might have across your input pins, or an RC network between the output and the input, or even just a capacitor between the output and the input. I'm talking about also the compensation capacitor in the LM301, the external comp capacitor. Obviously, the larger the value of that, the slower the slew rate. So depending on how small that value was and how these op amps are running, they could be running faster or slower. So yeah, I haven't really taken that into consideration until now. I'll tell you why I'm starting to think about other things. jfet inputs might be causing instability because they take way lower bias currents. This thing's obviously designed for BJT op amps. I know output drives usually a concern, but I don't think it is in this case. Although the transistors that drive the output are fairly low gain, like you got 2030 HFE on the outputs, and then you got that driven by another 2030 HFE transistor, and then that's driven by a smaller transistor, and that's driven by an even smaller transistor. The last transistor's gain's like 400 or something. So although the last two in the chain are low gain, I think the one before it and the one before that are making up for that. You know, it's basically triple Darlington. So I don't think the op-amps aren't sourcing enough current, but it also is a possibility. Because like one thing I said, can you not get in the box of wires? One thing I've said from the get-go, I've just gone off topic now, is that I've been suspicious that my op-amps are going out of range. And when I say out of range, I mean, say, input voltages versus rails, input bias currents, current that the output's expected to supply, stuff like that. And to be honest, I haven't had a really, really good look at it. Silly move, I guess, because this is like such an older design. Everything's designed for older, higher current bipolar technology op-amps. So all the bias networking and current considerations and dropper resistors are going to be a lot chunkier than what you're going to find in a power supply these days. And the layout's a bit different too. So I'm starting to wonder if you go get a power supply these days that's got some given op-amp in it, you probably find to stick anything in OPA7s, TLA72s, world of difference in accuracy there, but they'll probably both work in there, right? But with this, I'm starting to wonder, and I'm going to show you why. And I think it'll become pretty apparent really quick why. Because I think if I keep trying to do what I'm doing, trying to compensate op-amps, I don't think we're going to have any luck. And I think if I was to compensate it to the point that I got rid of all the noise, the slew rate would be like 1 volt per second. I'm not even being funny. And we'll get to exactly why that is in a sec. I'll show you. It's actually quite comical. So looking back at the output of this op-amp that compares the pot and the reference and spits that out to get compared against the op-amp that compares the output against the output of that. You've got to be shitting me. There's no way I just did that. Fuck. Oh, man. Finally did it. Yeah, that's gone. That is not how that looks. Oh, that's gone. I'm going to have to change that op-amp. I just took the soldering iron to its output with the negative terminal reference to ground on the scope, and the power supply was still switched on. I can't believe I just did that. I'll be back in a moment. I've got to change my op-amp. Sorry about this. I figured whilst I'm changing this op-amp, might as well have a little talk about what I wanted to talk about anyway. So last night I had a good scope around, and I'm going to show you a couple of things as soon as I get this op-amp changed. But basically, without putting basically absolutely insane values of capacitance across things, which would slow things down to the point that it would be unusable as a power supply, I couldn't get things to be quiet. So I'll show you what I mean, but basically I think we're going to have to put different op-amps in here, bipolar, and I'm going to particularly pay attention to the input bias currents, because I've got a funny feeling that that's got something to do with it. I could be wrong. I don't see any of the other specs on here really affecting it. Slew rate could be, but look, the old LM301s were pretty heavily compensated. I would imagine the slew rate of these would be, the way they are running open uncompensated, would be faster currently. So I'd imagine when I slow them down a bit, it would bring that into the ballpark as LM301, and it's not having an effect on oscillation, so I don't think it is that. I think we'll have a look at the data sheet after I've taken this chip out, and we'll just have a look at how much current the output can actually sink. I'm really starting to lose traces here. I can't keep taking opamps in and out. I mean, obviously I can fix it, but, you know, I don't want to be here for a million years trying to fix up all these little ripped traces, you know. Yeah, so I'm starting to think, honestly, that my best bet might be, let's leave that aside in case that's not the one I cooked, but I think it is. I think the best bet is to have a look through my inventory and find an op amp that matches the LM301 a little bit more, and just look, it's not going to affect the voltage accuracy, the way this thing's done, and because it's voltage. So the thing with constant current circuitry is you're sensing voltage across a current shunt resistor or a shunt, so it's a very small voltage. So then you obviously need low input bias, low input offset voltage, high accuracy op amps, the resistance of the shunt, the accuracy of the reference, all these things come into play. It's a lot more tricky to design a constant current circuit that's really accurate than a constant voltage circuit. So I might have to just accept it. It's going to be better than what it originally was, but I wanted to make it, you know, sort of like on par with your average couple $100 linear Chinese supplier that's, you know, fairly decent, but not like crazy good specs, you know. They're usually based on like anything from an LM358 to TL072s to OPO7CPs, stuff like that. But just depends how shit the design is and how cheap it is or how good it is. But anyway, before I keep wafting on, I'm just going to go grab another TL072. Probably just a complete waste. But what do you do? Well, I know what I'm going to do. I'm not going to short it out this time. I think I will pause the video now because I've said what I wanted to say and I don't want to bore people watching me put yet another op amp in. I'll be back in a second. Okay, the op amp that I just ground shorted has been changed. Let's see. Oh, fuck off. You're going to be shitting me. It wasn't that op amp. Oh man. Oh, you know what I did? I touched the soldering iron on the output of it. Oh, that's not good. That goes into a transistor. Shit. They're pretty solid transistors, but still. And 2N2270s. Oh, I'm in the amps game. I was like, nah. Come on, please, please, please. No, that's still alive. I didn't look at the voltage drop. Let me just compare the junctions. Yeah, no, that actually looks literally how they all look. Confused. I thought the output went down to this op amp. It doesn't. It goes to a transistor. God, this is such a head fuck. But it is tied in with the voltage pot, and that does go back to one of these op amps. So, but it's tied in on the input side. Man, seriously? If I wind the voltage all the way down to it, it's that op amp. I know which one it is. I changed the wrong op amp. God, that's bloody annoying, eh? That's really bloody annoying. Yeah, no, I'm pretty confident it's the constant voltage op amp I just clicked. Because the voltage is just pegging straight up, there's nothing pulling it down. Anyways, what I was about to show you guys on the scope before I just fried my board here was that last night the only way I could get the reference to be a little bit quieter with or without compensation on the op amp was to literally put 47 mic across it. Anything under that, you couldn't even see the waveform get a bit smaller. And here's why I say that I got to the point that I was like, this is just not viable. To compensate this op amp to the point that the noise goes down to an appreciable level with the power supply unloaded, took 1 microfarad. And not even one of these. I needed to get the lowest ESR 1 mic cap I could find, and it was just on the edge of being okay. And then still when I loaded it, it just got worse and worse and worse and worse and worse. I pretty much had the same experience all the way through the boards. Like, no matter what I add, it ain't doing nothing. So I pretty much arisen at the conclusion that I need to put all different op amps in here, but just for the purpose of so everyone knows what's going on, I'll pause the video, I'll change another op amp, and I'll come back and continue. Oh, you're not going to believe my luck, eh? It's not pegging all the way up now it won't go up at all. You know what I did? The first op amp I took out and I changed, when I realised it wasn't that op amp, I put that on the desk and I thought it was good. So I changed the second one with that. Yeah, it turns out I cooked them both. Oh my god. I'm having a good day today. Really good day. I just can't believe it. I've never spent this long working on a power supply in my life. Admittedly, I did waste a lot of time because I didn't look at the power layout. And I may have wasted more time just jump rushing and sticking TL072s in there without taking a few more of their parameters into consideration. So I got myself to blame there. But yeah. Anyway, I'm not going to bore you guys changing another op amp. I'll be back in a minute. Alright. I have now changed 2 op amps. Wish me luck. I haven't turned this on, honestly. You're seeing it with me. Finally. So it was both of them that I buggered. Alright, now, as I was trying to show you guys before I cooked 2 op amps, silly me. Actually, I don't know that I cooked both of them. I could have just cooked one. I'll leave these in the jar of components I pulled out, because obviously all the op amps I cooked, plus the original LM301s and other random things like resistors and capacitors and diodes and stuff, I'll test them all, and all the good ones I'll keep. Old parts I'll use for old stuff, and you know, my new parts, if they're good, I'll put back in my drawers. Right, where are we? So I want to be grounded to here. This is my probe that I've got. I'll turn this off, take that off. Don't want to make that mistake again. The reason I disconnected the ground probe, even though it's off, is because capacitors are still discharging in here, and it would not be good if there was still voltage on here and I shorted it and popped something. Right, so this is the hold on a minute, that's not right. I don't know if you guys can see all those lines. I don't know if I've got a loose connection. I think I might still have another problem here still. Because the peak to peak was exactly 20 millivolts and the RMS was 2 point something, about 2.5 millivolts. And now I've got 1.33 millivolts RMS and in between 18 to 182 millivolts peak to peak because of these huge spikes that are just randomly appearing. They definitely weren't there before. What else could I have cooked? It's my reference folder still here. Yeah. I'm going to put this into amps. I'm just going to short it and turn the light up and see. I'll just move this ground clip up to the ground on here for this circuit, same spot. That's what I was saying before. Just I could have it clipped anywhere, so it's just hard to give a straight answer on that. I'm gonna short this, put a load on it, and see if the constant current circuitry is buggered. No. Seems to be doing what it always does. Oh man, now I've got all these random spikes after doing that, and I don't know what they are. That's really concerning me. I don't know. I've just got this bad feeling that I've damaged something else. Let's have a look at the reference quickly. Sorry, this is really not where I meant to go with this. Honestly, even though there's spikes there, I can still kind of show you what I wanted to show you, but I obviously need to work out what's going on here. Oh wow, the spikes are there too. I'm wondering if I just damaged that TL431 that sits right here. Because I just cooked this op amp and this op amp, which are about 5 centimeters apart, and the TL431 sits in between them. And it's all part of the one circuit. Because there isn't really any active components in. I mean, there's a 1N4148 diode and a transistor. I'll just quickly test the transistor and see if any of its volt drops have changed radically, indicating that it might have changed characteristics and have a problem. Oh, that has changed. What the hell? Is that transistor warm? Okay, the transistor's warm, that's fine. I forgot about that, those transistors get warm. It's only dropped by about, it was around 600 millivolts drop. It's about 550 now. That's just because it's warmed up. I mean, I could test the diode that's across here. I'm not going to really see it if it's making random spikes on a multimeter anyway, but let's just see if it's changed radically. No. I've got a funny feeling that I've just damaged. Oh, hold on. Oh, this is the best news ever. Those spikes are there with the power supply turned off. Oh, I'm an idiot. You know what it is? It's my bloody desoldering gun. It's bloody triac pulsed. I don't even know if you guys can see these spikes. Yeah, that's what I'm talking about. Just put this here. Might be more helpful for you guys. Well, then you can't really see what I'm doing. Guess these leads are kind of in your way too, eh? Alright. Okay, let me turn my desoldering gun off. Oh, what do you know? The triac looking pulses have disappeared. Wonderful. You know what? That's really wonderful because I don't have to change another part. I thought my TL431 had broken down and was just firing random pulses. I couldn't think of anything else. It's active circuitry that's just bridged something. That could be doing that really. Beautiful. Right. Something else I tried doing last night, as I was saying before, I've destroyed the op-amp. I was just about to show you guys what's going on with it. And last night, I was trying to compensate 20431, like I said, until if I try high frequency suppression or snubbers, I get absolutely no effect. If I put an electrolytic on there, I get an effect. If I, how do I explain it? Go up to a ridiculous figure like 47 mic, which being fed through like a 1.8k dropper resistor is going to create a bit of a time constant on power up that I don't want there. Especially when there's only 10 volts available to it. Oh no, that's the top one I'm thinking of. The bottom one's got 37 milliamps. Still, I don't want to create time constants all over the place. So, here's what I wanted to show you guys. This is what really sucks. Going back to the output of the op-amp that I just screwed before. And we have that. Now, that is with a 1 mic MKT, so really low ESR, lower than a monolithic capacitor. That's 1 mic. With that removed, we get that 5.65 millivolts RMS, 52 millivolts peak to peak. I could make the waveform a little bit bigger, sorry. There you go, 10 millivolts of division. Right, so with the cap, we drop down to 2.7-ish millivolts, 2.75 RMS, and around 20 to 22 millivolts peak to peak. So about half. And like I said, that's taken a whole 1 microfarad from the input to the non-inverting input. The output, sorry, to the non-inverting input, which is, you can't just go sticking figures like that on op amps. So, next thing. The capacitor I've put here on the reference, 47 mic. So as you can see, it gets rid of noise there too. But I've got to go up to 47 mic, you know. And for those that are curious what the op amp looks like compensated without the reference, like that. And then when you add the 47 mic, it just gets a smidgen smaller, you see? That's what I'm saying. This is what I'm getting at. It's ridiculous values just to see a result. And here's where it gets worse. That was unloaded. I load it down. I'm probably at like 200 milliamps. Not even 100. That's 100 milliamps. Can't live with that. You know. So with all that comp on the op amp. Oh, and trying to put a snubber or a compensation network from the op amp's input pins across each other, that only couples the noise from one input to the other and makes it literally a million times worse. The TL431, I tried decoupling its reference pin. As I was saying earlier on or in my last video, I don't know if I finished explaining what I was saying because I just waft off topic all the time. It's something I'm good at, but I got a bit of experience playing around switches and stuff like that, and a lot of times, I'll just grab one just to show you what I'm talking about. You might notice that there's a TL431 here, going to a 3-terminal opto isolator, so it's got the bass pin pulled out. But anyway, that's not what the interesting part is here. You might notice that there's a little compensation snubber network in between the reference pin and the anode, or is that the cathode? I'm not sure. Hold on, that's the cathode. In between the reference pin and the cathode, there's a snubber network there. So a lot of the times in certain applications, you need to do stuff with the reference pin. I tried pulling the reference pin via snubbers to both the anode and the cathode, and let's just say one made no difference and one just coupled more noise into it. So as far as the reference and that op amp there is concerned, what you're saying, a 47 mic cap and a 1 mic cap is literally all that can be done to it to make it just a little bit more quiet, and it still doesn't change jack shit. So moving back over to the first stage, we'll look at the output of the op amp that is looking at voltage. I'm doing this all on the master channel. Alright, So 3.2 millivolts RMS, 25 millivolts peak to peak. Again, high frequency garbage. Very high frequency. I just thought I'd zoom in on it just in case anyone wanted to have a clearer look at what's going on. I'd probably be able to see a lot more if I had a better scope. This is only 100 meg scope, but yeah. So that's the output of the constant voltage op amp. Now I'll just take in my hand in between the output, and you know what, I'll solder it. Between the output and the non-inverting input, I'll just put a 100 nanofarad capacitor there. I know it's a really big value and it could couple mains noise into it, but I'm sure for the educated people here, including everyone that's probably watching this channel and myself, I think we'll know if we see mains ripple compared to high frequency noise. So, not really worried about that. Nothing's changed, right? And that's literally 100 nanofarads from the output to the input. And I wouldn't even, that's a ridiculous value. You know how much that's going to slow it down? That's unacceptable. Like, by no means is that in any realm acceptable. Let's actually have a look what it does when we load it, just out of curiosity. Just goes absolutely ballistic. It's really not good. And as you can see, when you do a slow acquisition, that was actually me moving the tweezers around. I thought the frequency had like different components to it, but no. So anyways, I'll move to the output of, well, actually before we do that, let's just take what I've got here should be a 1K resistor. I can guarantee this is not going to make a difference, but we'll try. It's a very stiff snubber. Laid it down. Yeah. Alright. Excuse me. So, give up on that approach. I'm going to move it in between my inverting and non-inverting input pins, and yeah, I'm still leaving the resistor there as a snubber because it's 1K, it's going to work either way. Anyway, as I was explaining, you couple more noise from one input pin into the other and it gets worse. So, no. You'll see what I'm saying about the fact that I'm going to have to put different op amps in here, right? But we'll still keep going, because you never know, we might come across something that's the source of it and, you know, it all turns out all well, but I doubt it at this point. The way the panel meter kicks back and I've just seen too many things that has made me say repeatedly over and over again, oh, I think it's going out of range, like one of the parameters of opamps. And you know, you know when you keep getting the same thought or you got a gut instinct, it's usually right. So, you know, so that's the constant current opamp. Put a load on it. Hey! Bloody cats. Ooh, straight into oscillation. Same thing, right? So we'll put 100 nano 1K from the output to the input on the constant current op amp. Okay, well, I think it might be a bit smaller, but I'm not sure. Ugh. Fuck. Jesus. Winding it up, and yeah. These are not going to be compensatable. It's just not going to happen. I mean, I will try one other thing, just quickly. I'm just going to go between the two inputs now, with the 100 ohm resistor and 1 nanofarad cap snubber. As expected, just couples noise from one input to the other. So what I'm going to do now is just my last ditch effort. I'm going to go grab some very, very small value capacitors. You know, 1 nanofarad, 100 picofarad. One moment. So I'll just pause the video so he's waiting. Alright, I got a 10 puff and a 100 puff disc ceramic. And the reason for that is to go across input pins. Obviously, this will be useless going from the output to non-inverting input, given this scenario. But just for high frequency suppression without coupling everything else from one pin to the other, this sometimes does the trick. But I'm not going up in values beyond this because it's just going to slow it down. There's no point in trying to make something faster and then put capacitors in places that slow down the performance of the circuit, right? So that's 100. Oh, and that's on the input of the non-inverting and inverting input of the constant voltage op amp, the first one in the chain. I thought I was onto something for a second, and I realised my thing was just turned down. It's exactly the freaking same. Wow. Yeah, that's literally like nothing. And it's way worse. Way worse. Alright. I'll put a 10 puff on there. But beyond this, I've already tried sticking caps across the reference on the top board to no avail. and the only other op amp on there is the one that drives the panel meters, and that just appears like it's out of range. Like I've got to redesign the the input bias circuitry. So I was already thinking about just putting 2 different op amps in there just for the panel meters, because I'm not so fussed on the accuracy of them so much. Like I am, but not to the degree that I am with the regulation itself, of course. Alright, 10 picofarad across the inputs. Yeah, the same there. Yeah. I think you will get the drift to why I'm saying let's ditch these op amps, because I think they're, without redesigning basically half the fucking circuitry in here, changing a whole load of resistor values, literally calculating everything from scratch. I'd even have to change transistors, because they might actually be presenting too much of a load. There's a lot of stuff that I'd have to go through. It'd be basically just like what I'm already doing. I'm already engineering my own supply from scratch. I'm not going to do 2. I think the best thing to do is just to put different op amps in here. Let's just try the same thing I just tried on the other op amp for the current, but I think we already know it's not going to make a difference. $100 picofarad there for now. On. Yeah, nothing's changing. Alright. Need I try 10 picofarad? Not really. But look, at really high impedances, shit, I've lost it now. At really high impedances, even 100 puffkin, couple mains, ripple and stuff like that, and lower frequency harmonics, in and out of one input and into the other. So I will go down still one more time and try this, but beyond this, I'm putting different op amps in here. I just don't see this ever working with these op amps. Yeah, no different. I don't even need to continue. Yeah. So, alright, let's take all this off. I'm just going to touch up quickly everything that I've been tacking on and off of, because I'm starting to get dry solder joints. 1 second. And if I don't do it now, I'll forget about it, and it'll haunt me in the future. Suspicious. Yeah. Oh yeah, the input pins. Okay. So let's now look at data sheets, because like I said, unless anyone's got some suggestions that is ahead of me on this, obviously I don't know everything, there's definitely people that know more than me. If anyone's watching and you think it's not what I think it is, which is the wrong opamps, let me know. But I cannot see any means of compensating these. So I was just having a look at some crappier opamps that I've got to see like what they are like compared to the ones that were originally in there. But internally frequency compensate for unity gain. Yeah, so this is a totally different kettle of fish. Still got really small input offset and bias currents. Wait, are these things like rail to rail? Am I reading this wrong? Surely not. I might have to go do this in my own time because I've got quite a few different data sheets to compare different things on. But swing, voltage in 5 volts, the load's 10k, 5 to 20 millivolts, is that of each rail? That's good. I have to double check on that because I could be completely wrong. Oh, output voltage swing, is that? Oh, I see what's going on here. It's are they saying it's like over 26 millivolts from the positive rail and 5 to 20 from the negative rail? I don't know. I'll do some research on that just to make sure I'm not reading that wrong. But the input bias currents in the nanoamp region, I think more microamp. Where's the LM301? One sec. Oh. Okay. Interesting. Alright, well, I'm going to go compare a few different data sheets because I have got tons of components. I've probably got like 30 different types of opamps in here. I'm going to go compare data sheets and work out what opamp I'm going to use. It's not going to be jfet input. I got a funny feeling the main problem I've actually got here more than the topology of the op-amp is the jfet inputs themselves. I could be wrong, but they just jfets are very sensitive devices. There is a linear region on them, but it's not hard to get them outside of that, and oscillation, all that sort of crap would do that, which would then make the whole op-amp do weird things and go out of range, like what the panel meter is doing. So that's why I kind of think it's something more to do with that. But I'll go compare specs like input offset voltage, input bias current, slew rate, everything that's important, the output voltage swing, how much current it can source and sink, and I'll choose out something that I think's basically going to do the job. Hopefully I can find something better than what was already in there, and I guess I'll come back and we'll do that. I mean, I'm not going to give up on it. I'm going to get it going. It's just, yeah, I wasn't expecting it to take this long, so it is what it is. All right, well, I'll leave it for here. I'll be back when I've worked out my new set of 8 opamps. Thanks for watching. Bye.